In this one, you're being asked to draw the products of the following acid-base reaction below. And then you're going to label each compound as the acid, the base, the conjugate acid, or the conjugate base. And then we're going to determine the direction of the equilibrium. All right, so just like the last example, 1A, in this one, we're going to first figure out which species here is acting as the base and which one is acting as the acid. Again, the species with the negative charge, it's more basic. It has a full negative charge. It's going to send those electrons out to pick up a proton. So this will be our base here, which means this species is our acid. So we can label those right away. We'll say base, and we'll say acid. And just like the last example I mentioned, you can figure out which protons are most acidic in the acid if you know the pKa. So the pKa of a carboxyl proton is about 5, and the pKa of these protons on these carbons, they're going to be about 50. The lower the pKa, the more acidic the proton. That means that this proton is the one that's going to get removed because it has a pKa of about 5. Okay. Again, you can look at the conjugate base of each to figure out which one is most acidic. So here's what I mean by that. I'll do this a few times in a few of these examples. So if we want to figure out which one is most acidic, we'll look at the conjugate base. So there I'm removing the proton on the oxygen to look at that conjugate base. And then I'll remove a proton from one of the carbons here. And let me duplicate this. And we'll look at these 3 species here. So in this one, and this one. So these are all the places that the negative charge can exist, right? And we want to figure out which proton's most acidic. Well, we'll look at these conjugate bases and we'll compare them. Here are the negative charges on oxygen. And in here, the negative charges on carbon, carbon, and carbon. Well, we're just going to ask ourselves, where's the negative charge more stable? Which atom is handling that negative charge better? It's the oxygen. It's more electronegative. It'll handle that extra electron better, which means this is most stable, which means this proton is more acidic. So it's not going to be any of these species here. So again, that's the way you can kind of do this using the pKa, but if you don't know the pKa's, you can still figure out which proton's more acidic in most cases. All right, so we have those 2 species labeled. Now we're going to figure out what the products are. Well, the base is going to remove this proton, and it's going to leave both of these both of those electrons behind. Remember, one of those electrons already belongs to oxygen. The other one belongs to the hydrogen. That's why the oxygen ends up with a negative charge, because it's getting the electron that belonged to the hydrogen. When that base removes that proton, it's going to form the conjugate acid of that species, which would just be methanol in this case. So here is the conjugate acid, and here is the conjugate base. All right, so we have everything labeled here. Now we want to figure out what is the direction at equilibrium. So again, we can go by using the pKa method. We can kind of say, all right, well, this species has a pKa of about 5. This acid has a pKa of about 18. Well, the more acidic acid has the lower pKa, which means the equilibrium is going to shift away from that one. So that lets us know that if the acid with a pK of 5 is more acidic, that means the equilibrium is going to go this way. The other way we can do this, if you don't want to memorize pKa's, is we can look at the stability of both bases. And we're just going to ask ourselves which one's more stable. So we're comparing these 2 species. Both of them have a negative charge on oxygen. This negative charge on oxygen, it is stuck there on that oxygen. The negative charge on this oxygen, it's actually being stabilized. And it's being stabilized via resonance. So what we can do is we can see that this negative charge, it's moving around. And that's going to help stabilize it. So this negative charge can move here and kick these electrons up here. And what that means is that negative charge is not fixated. It's not localized on one oxygen atom. It's being delocalized. Resonance is typically stabilizing. So that means this conjugate base is more stable, which means it's more easily formed. This one is not as stable, so it's more basic, it's more reactive. So again, that's just another way of saying the equilibrium is going to shift towards the more stable conjugate base.